Good morning, children. So, I am very happy to share my experience with you, and also I am very impressed the way you received the video last video in Boyan Study Circle. I request all of you to hit the like button whenever you watch the video, and also I request you to subscribe our channel to bring you very important topics which are useful for you. So, I request all of you once again to subscribe. By that, you will get encouraged to bring different videos for you. So, today our topic is atomic structure part 2. As I promised you, I want to discuss the second part, that is Sommerfeld's model. Sommerfeld's model. So, in the last video we discussed Rutherford-Thomson model, Rutherford's model and Bohr's atomic model, and we discussed the last model, that is Bohr's atomic model. So, there were some drawbacks, that is splitting of spectral lines when the spectrum is recorded in the presence of magnetic field or electric field. So, this was not explained by Bohr's model. So, for that Sommerfeld came forward to explain the splitting of spectral lines by introducing elliptical orbit concept. Elliptical orbit concept, right. So, he retains Bohr's first orbit as circular. Then he added elliptical orbit. So, as per the Bohr's model, all the orbits around the nucleus are circular, but he introduced the elliptical orbit concept. He retains the first orbit as the circular, and then he adds the elliptical orbits. Further we move on. For example, you take n is equal to 1, that means first orbit as per the Bohr, right. So, the first orbit is circular, right. So, that means circular orbits are 1 and elliptical orbits are 0. That means, if there is only one orbit, that should be circular. When there are two orbits, one is circular and the second one is elliptical, right. So, the circular orbits are 1 and elliptical orbits are 1, right. And when n is equal to 3, right. So, there is one circular orbit and there are two elliptical orbits, right. So, that means circular orbits are 1 and elliptical orbits are 2, total 3, right. So, in the same way, when n is equal to 4, one is circular orbit and there are 3 elliptical orbits, right. So, circular orbits are 1 and elliptical orbits are 3. So, in this way he introduced elliptical orbit concept, right. So, when you are asked in the examination, if there are total number of orbits 2, how many elliptical orbits are present? You minus 1, take minus 1, that means if the total number of orbits are given 2, you just subtract 1. So, that is the one circular orbit, the remaining are elliptical orbits, right. So, if n is equal to 4, how many elliptical orbits are present? So, 4 minus 1, 3 elliptical orbits are present. So, in that way he proposed the elliptical orbit concept, and using this he can explain the splitting of orbits, right. So, splitting of spectral lines can be successfully explained by the Sommerfeld's model of atom by introducing the elliptical orbit concept, right. But here also some drawbacks, right. So, even though even though it explains the splitting of spectral lines in the presence of electric and magnetic field, it could not give complete explanation about structure of atom. So, that means up to now we have discussed Rutherford's model, Bohr's model, and then Sommerfeld's model. Did you get any clarity about the arrangement of subatomic particles, electron, proton, neutron? No. So, there is no clear explanation about the arrangement of subatomic particles. So, that is why it could not give the complete explanation of the structure of atom. Number 2, it could also not explain spectrum of elements with more than one electron. So, this drawback was also already there in the Bohr's model. So, here also he could not explain the spectrum of atoms with more than one electron. That means, this model can also explain the simple spectrum of hydrogen, but it cannot explain the atoms which are having more than one electron, right. So, this is about the Sommerfeld's model. And then children, if you want to take the notes, you just take the screenshot of this, and later on you can note down the points, right. Next, so children, here we have a question that do the electrons revolve in defined paths as said by the Bohr, right. If they want to, if they are revolving in the defined paths, okay, you can able to find out their exact position and velocity. If they are revolving in defined paths at any time or at any contest, you can find out the exact position and velocity of the electron, right. So, as electron is invisible, that means you cannot see the electron with your naked eye, right. For example, if you want to see the items in the dark, you need a torch. Just like that, the electrons are also not visible with your naked eye. So, you need a light to see the electron. As the electron is a smaller one, very smaller one, so you need a short wavelength light, So, when you focus the short wavelength light on the electron, you know that light is associated with energy. So, when you focus this light on the electron, it gets energy and its velocity increases, it moves from its original position. That means, its position is changing and its velocity is also changing. So, by this a small experiment you came to know that you cannot find the position and velocity of electron, you cannot find position and velocity of electron could not be find simultaneously and exactly, right. So, when you focus the light on the electron, it gets energy and its velocity increases. That means, now the velocity calculated is not its original velocity and the position is also not its original position. So, if you fix the position, velocity is changing, if you fix the velocity, position is changing. That means, you came to conclude that the position and velocity of electron could not be found simultaneously and exactly, right. So, in the same way, is there any boundary for electron? Is there any boundary for electron in the path? Right. Right. So, when electron is revolving in the circular orbits, is there any fixed boundary? Right. So, according to that means to explain this, a quantum mechanical model proposed by Erwin Schrodinger. So, quantum mechanical model as proposed by Erwin Schrodinger, right, to explain about the behavior of electron in the path, right. So, who proposed the quantum mechanical model? Erwin Schrodinger proposed the quantum mechanical model, right. So, now you came to know that you cannot find the velocity and position of electron simultaneously and exactly. So, that means electrons are said to be found in a region or in a space, in a particular space or particular region right. So, that means you cannot exactly pinpoint the position of electron in the path or in the circular orbit. So, you can find the space where the electrons probably find out. So, there is a particular region where you can find the electron around the nucleus. So, that space around the region, space around the nucleus, the region where you can find the probability of electron is maximum, or the region around the nucleus where the probability of finding electron is maximum is called orbital, right, orbital, right. So, that means that there is no particular boundary for the position of electron. It can probably find in a space around the nucleus, right. So, that space of region around the nucleus where the probability of finding electron is maximum is called orbital, right. So, this orbital is introduced by quantum mechanical model. Now, Erwin Schrodinger gave an equation that is called Schrodinger wave equation. Schrodinger wave equation. So, that Schrodinger wave equation is dou square psi by dou x square, dou square psi by dou y square, dou square psi by dou z square plus 8 pi square m by h square E minus V psi is equal to 0, right. So, this equation is called Schrodinger wave equation. Children, no need to remember this or no need to mind this, just you listen the equation. So, this is called Schrodinger wave equation. Dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 8 pi square m by h square E minus V psi is equal to 0. What I am mentioning here, this equation means by solving this, right, quantum mechanical model derives a set of quantum numbers, which gives the complete address or complete information about the electron, right. So, when you are asked to how the quantum numbers are arrived or how the quantum numbers are derived, then you have to answer that by solving the Schrodinger wave equation, the quantum numbers are derived or quantum numbers are arrived by solving the Schrodinger equation that you have to answer, right. So, now we are going to discuss the quantum numbers by which you can explain the address or the nature of electron completely in the given orbits, right. Quantum numbers. Quantum numbers. So, the first quantum number is principal quantum number, right. Children, I will write the all points here one by one. If you want to take the notes, please take the screenshot and then note down the points in the notes, right. So, principal quantum number. So, it was proposed by Niels Bohr, right. So, it was proposed by Niels Bohr. It is denoted by letter N. It is denoted by letter N, right. N has values 1, 2, 3, 4, so on, K, L, M, and so on. Already we have discussed the Bohr's atomic model. There he said the electrons are revolving around the nucleus in circular paths called orbits or energy levels. So, he named those orbits as 1, 2, 3, 4 or K, L, M, N and so on, right. That means, you came to know that this quantum number explains the main shells or the main orbits or the main energy levels present in the atom, right. So, that means it explains about energy and radius of the main shells, right. So, for example, or when you observe this, this is the nucleus, first orbit, second orbit, third orbit, fourth orbit, like that. So, if you want to number 1, 2, 3, 4, K, L, M, N, right. So, these are the orbits. So, that means if n is equal to 1, if you are naming the principal quantum number 1 means it is the first orbit, or if you are naming it as K means it is the first orbit, right. So, you observe, so this is the nucleus, and from the nucleus to the distance from the nucleus to first orbit is called the radius of the first orbit, and in the same way radius of the second orbit, radius of the third orbit and radius of the fourth orbit. So, that means as you are moving from the nucleus, the distance of the orbit increases, that means the radius increases, right. So, in this way you can find out the radius of the orbit, and you know that every orbit or energy level is associated with some amount of energy. So, as we are moving away from the nucleus, the energy of the orbit increases, right. So, if you want to find out the radius and energy of the orbit clearly, we have some formulas. If you want to find out the energy of any orbit, n is equal to orbit, right. So, minus 2.18 into 10 to the power of minus 18 z square by n square joules, right. So, this is the principle to calculate the energy associated with a given orbit in joules, right. So, minus 2.18 into 10 to the power of minus 18 z square by n square. Observe here, z means atomic number, n means the orbit for which you want to calculate the energy, right. So, for example, if you take the hydrogen atom, right. So, the atomic number of hydrogen is 1. So, if you substitute 1 here, it will become 1 square means 1, and if you want to find out the first orbit energy, n is equal to 1, it also 1 square 1. So, z square by n square become 1, and the energy associated with the first orbit is minus 2.18 into 10 to the power of minus 18 joules. In this way, you find any orbit and in any element, any orbit, any element. For example, if you want to find out the helium, substitute the atomic number of helium 2 here, and then if it is the helium's first orbit 1, helium second orbit 2, in that way for any element, for any orbit, you can calculate the energy associated with the orbit, right. And in the same way, if you want to find out the radius, right, 0.0529 into n square by z nanometers, right. So, nanometers, in nanometers you can find out the radius also. For example, n square means here it is the orbit number and z means atomic number. For example, if you want to find out the radius of the first orbit in hydrogen atom, so z is equal to 1 and 1 square means 1, that means 0.0529 nanometers. So, in this way you can find out the energy associated and the radius of the orbit of any element, right. So, that means up to now you came to know that this principal quantum number explains the main shells present in the orbit, present in the atom, and their energy and their radius, right. And also the maximum number of electrons that can be filled in main shell is given by the formula 2n square, right, 2n square. For example, if you are taking the first orbit, how many electrons can be filled into the first orbit? What are the maximum number of electrons that can be filled into the first orbit? So, first orbit means in n square place you can substitute 1. So, 2 into 1 square, that will become 2. So, that means in the first orbit only 2 electrons can be filled, right. If you take the second orbit, 2 into 2 square, that means the maximum electrons that can be filled into the second orbit means 8. And in the third, 2 into 3 square, 18 electrons, and in the 32 electrons, 50 electrons. In this way you can fill the electrons in the main shell, right. So, in the main shell, the maximum number of electrons that can be filled can be given by the formula 2n square. Here n is the principal quantum number. That means, if you take the first orbit, the maximum number of electrons are 2, and second orbit 8, third orbit 18, and fourth orbit 32, and fifth orbit 50 electrons. In that way you can count for any orbit the maximum number of electrons that can be filled into the main orbit, right. So, these are some important points that can be covered under the principal quantum number, right. So, next we are moving to the second quantum number, that is Azimuthal quantum number. Azimuthal quantum number, right. So, it was proposed by Sommerfeld. It was proposed by Sommerfeld. It is denoted by letter L, right. So, it was proposed by Sommerfeld and it is denoted by letter L, right. So, L has values equal to n. L has values equal to n and ranges from 0 to n minus 1, 0 to n minus 1, right. So, what does that mean, right? For example, this quantum number explains the subshells and their shapes, right. So, already in the principal quantum number we discussed the main shells, right, that means a main rod, right. Then entering into the main rod, there are some sub rods or side rods. In the same way, when you enter into the main shell, there are subshells, right. So, what are the subshells present inside the atom, right. So, for example, the number of subshells in a main shell is equal to n, right, is equal to n, right. For example, you take the main shell 1, that means the first orbit, right. So, in the first orbit, the number of subshells present is equal to n, that means n is equal to 1 here, that means only one subshell is present. That one subshell is nothing but 1s, right. So, in the first orbit, what is the subshell present? S is the subshell, as it is present in the first, that is called 1s. If we take the second subshell, second main shell, the number of subshell present is equal to 2. So, they are 2s, 2p. And if you take the third subshell, right, the third main shell, there are 3 subshells, they are 3s, 3p, 3d. If you take the fourth main shell, there are 4 subshells, so 4s, 4p, 4d, 4f, right. So, in this way, there are subshells s, p, d, f. So, these are the subshells present in the main shells. So, about these subshells, this quantum number is explaining, right. So, in the first main shell, the number of subshell is equal to n value, that means only one subshell is present, as it is the first main shell, that is 1s, as it is present in the 1s main shell, first shell. So, if you are taking the second main shell, there are 2 subshells, so they are named as 2s, 2p, as they are present in the second shell. And in the third main shell, 3 subshells are present. So, they are named as 3s, 3p, 3d, right. And in the fourth main shell, there are 4 subshells, 4s, 4p, 4d, 4f, right. For example, why there is no 2d? Why there is no 2d? Because second main shell has only 2 subshells, they are s and p, there is no chance for the d, that is why there is no 2d. Why there is no 3f? Because in the third main shell only 3 subshells are present, that is why 3s, 3p, 3d are present, there is no 3f, right. So, in this way subshells are present, right. And what are the values of these subshells, right. So, for subshell S, L value is 0, for subshell P the L value is 1, for subshell D the L value is 2, and for subshell F the L value is 3. Right. So, as we discussed, the L has values equal to n, right, equal to n. That means, if we take the first main shell, right. So, what is the subshell present? S, right. So, the value starts from 0. So, that is why 0. And in the second subshell, what are the present? Second main shell, what are the present? 2s and 2p, right. So, total values are 2 and 0, 1, right. So, p has 1. And in the third main shell, 3 subshells are present and their values are equal to 3 and they start from 0, 1, 2. So, d 2, right. And fourth main shell, 4 subshells are present. So, total values are 4, starts from 0, 0, 1, 2, 3. So, f has L value 3. In the same way, so you have to remember that S L value is 0, for P L value is 1, and for D L value is 2, and for F L value is 3. And also it explains the shapes of the orbitals, shapes of the subshells also, right. So, S subshell has spherical shape, and P subshell has dumbbell shape, and D subshell has double dumbbell shape, and F subshell has a complex shape, right, complex shape. So, in this way, the second quantum number, that is Azimuthal quantum number, explains about the subshells present in the main shells. So, you came to know that there are 4 subshells S, P, D, F, they are present inside the main shells, right. Their L values and their shapes are present, and this quantum number is also called as angular momentum quantum number, right. So, this quantum number is also called as angular momentum quantum number, right? Okay. So next we are moving to the third quantum number. Third quantum number, that is magnetic quantum number. Magnetic quantum number, right? Magnetic quantum number, right? So it was proposed by Lande. It is denoted by M. Okay. So it is denoted by M, right? It has values 2L plus 1 values, 2L plus 1 values ranging from minus L to 0 to plus L. So it starts with minus L and goes through 0 and then up to plus L, right? So this explains, right, the orbitals present in the subshell and their orientation. So this is the significance of this quantum number, right? So we start with principal quantum number. Principal quantum number gives the main shells. When you enter into the main shell, there are subshells, they are SPDF, right? So that explained by the Azimuthal quantum number. And then when you enter into the subshell, there are some orbitals. So what is the definition given for the orbital? The region around the nucleus where you can find the electron more probably, right? So those are called orbitals. Those orbitals are present in subshells, right? And their orientation can also be explained by this quantum number, right? For example, if we take the subshell S, its L value is 0. Its L value is 0. When you substitute the L value 0, 2 into 0 plus 1, that means only one value is present, that is 0. So it is L value and these are the M values, right? Right? So when you take the subshell P, for L, for P, what is the L value? 1, right? When you substitute the value L in this 2L plus 1, 2 into 1, 2 plus 1, 3. There are total values 3 and they are starting from minus L, 0 to plus L. So minus L means minus 1, then 0, then plus 1, right? So that means how many orbitals are present based on the values. There are 3 values, that's why 3 orbitals are present in the P subshell and they are oriented along Px, Py and Pz, right? So if we take the D subshell, the L value for D is 2. When you substitute the L value 2 here, 2 into 2, 4 plus 1, 5. Total 5 values are present. And then they starts with minus L, that means minus 2, minus 1, 0, plus 1, plus 2. How many values are present? 1, 2, 3, 4, 5 values are present. So there are 5 orbitals in D orbital. So their orientation is dxy, dyz, dzx, dx square y square and dz square, right? And if we take the F subshell, the L value for F subshell is 3, right? So when you substitute the 3 value, 2 into 3, 6 plus 1, 7 values are present and they starts from minus L to plus L. So minus 3, minus 2, minus 1, 0, plus 1, plus 2 and plus 3. There are 7 values. That means there are 7 orbitals are present in P orbital, right? Sorry, F orbital, right? So in that way you can find out how many orbitals are present and what is their orientation, right? So for F subshell, L value is 0, so there is only one value, that means only one orbital. In P, L value is 1, so 2L plus 1, that means 3 subshells and 3 orbitals are present, they are Px, Py, Pz. And in D, 2 into 2 plus 1, 5 values are present, so 5 orbitals are present. And in F3, 2 into 3 plus 1, 7 values are present, so 7 orbitals are present. Then you know that each orbital can accommodate 2 electrons. So here 1 orbital, so the maximum number of electrons that can be filled into S subshell is 2. And there are 3 orbitals, so 3 2s are 6. And there are 5 orbitals, 5 2s are 10. And there are 7 orbitals, 14, right. So in S orbital, the maximum number of that can be filled are 2, and in P orbital, 3 2s are 6, the maximum number of electrons that can be filled into P orbital are 6, and in D, 10 electrons can be filled, in F, 14 electrons are filled, right. So in this way you can find out the maximum number of that can be filled into the subshells, SPDF. And then when you observe these 3 orbitals or these 5 orbitals or these 7 orbitals, are they having the same energy? Yes, they are having the same energy, because they are present in the same main shell, they are present in the same subshell. So as these 3 orbitals Px, Py, Pz are present in the same subshell, they are having same amount of energy. And these 5 are also same energy, these 7 are also having same energy. That is why the orbitals associated with the same energy are called degenerate orbitals. Degenerate orbitals. What do you mean by degenerate orbitals? In P subshell, there are 3 orbitals with same amount of energy. That is why these 3 orbitals are called degenerate orbitals. And in the same way, in D, 5 orbitals are present with the same energy, degenerate orbitals. In F, there are 7 orbitals with the same amount of energy. That is why they are also degenerate orbitals, right. So up to now, main shell discussed with the principal quantum number, subshells discussed with the azimuthal quantum number, and among them orbitals are discussed with the magnetic quantum number, right. And the fourth quantum number and the last quantum number is spin quantum number, right. Spin quantum number, right. Spin quantum number. Spin quantum number. So it was proposed by Uhlenbeck and Goudsmith. Uhlenbeck and Goudsmith. It is denoted by letter S, right. So it describes spin of electron, right. So as you know that each orbital can be filled with 2 electrons maximum. One electron is having clockwise orientation and another electron is having anti-clockwise orientation. So clockwise and anti-clockwise. So clockwise, if the electron is represented clockwise, its spin value is +½ and if it is anti-clockwise, the spin value is -½ right. So in this way, these 4 quantum numbers, principal quantum number, azimuthal quantum number and magnetic quantum number and spin quantum number, gives the complete address of the electron, right. For example, I give you, or how can we write the quantum numbers for a given element. For example, I want to write sodium's 11th electron quantum numbers, right. So later on we come across the electronic configuration, but I am trying to explain how to write the electronic configuration, how to write the quantum numbers, right. So the electronic configuration of sodium is 1s2, 2s2, 2p6, 3s1, right, 2, 4, 10, and this is the 11th electron. This is the 11th electron, right. So this is the 11th electron, right. So here this 3 indicates the principal quantum number, n is equal to 3. That means this 11th electron is present in 3rd main shell, 3rd orbit, right. And this S means L value. For S, L value is 0. So L value 0 means it is present in S orbital. When L value is 0, M value is also 0, right. L value is also, M value is also 0. And what is the spin quantum number? Only one electron, and clockwise that is plus half. So, the 4 quantum numbers n is equal to 3, L is equal to 0, M is equal to 0, S is equal to plus half, right. So, in this way you can write the complete address of the electron using these 4 quantum numbers, right. If you want to write the 6th electron in carbon, 6th electron in carbon, right. So, what is the carbon atomic number? 6. What is the electronic configuration? Right. So, 1s2, 2s2, 2px1, 2py1, this is the 6th electron, right. This is the 6th electron, right. So, as you said, this is present in second main shell, and P indicates the L value 1, for P L value is 1, and M value, right. So, there are 3 orbitals, you know that, plus 1, 0, minus 1, right. So, there are 3 orbitals, for example, 1, 2, only 2. So, Py, that means 0, right. So, S is plus half. So, in this way you can give the quantum numbers for any electron in the any element, for any electron, for any element you can write the quantum numbers. So, quantum numbers gives the complete address of the electron in the atom, right. In the next class we will discuss how to write the electronic configuration of elements, and also we want to discuss the nature of light and some of the important characteristics of the light that are associated. Okay, thank you very much, and don't forget to hit the like button if you like our video, and share with the maximum of your friends, and also subscribe our channel. So, once again I will wish you all the best, and thank you, and stay tuned to Boyan Study Circle. Thank you.